Yeah, so today we'll talk about reinforcement learning. It's a new, exciting topic. It will be mostly a review. There was a tutorial yesterday that I think some of you attended. We'll go over similar things, and hopefully this is mostly a review for you, but we'll go into into quite some detail into some of those reinforcement learning concepts. First, a few reminders. So today the project proposal is due. This should be mostly helpful to you. This will be a rather light review, but we want to make sure that the project proposals kind of make sense and you're on the right track to doing something exciting. And then another reminder is that homework 2 is due on Monday next week, and also homework 3 will be out on Monday as well. All right. So reinforcement learning is a new topic in this class. So I first wanted to start with, why should we care? Why should we work on reinforcement learning? And reinforcement learning is a field that deals with predicting long-term consequences of your actions and then learning intelligent behaviors based on that. And I was thinking, how to introduce reinforcement learning, and I was thinking of maybe showing some applications that you might have seen already, robots grasping, doing all kinds of different things, and so on. But actually, I thought that maybe we could reverse that question. And given that reinforcement learning deals with long-term consequences of your actions, maybe we can think of actions that are isolated that don't affect the future, right? So if we figure out what are those kind of settings, then reinforcement learning would deal with everything else. And actually, thinking about this, it's quite tricky to think of an action that doesn't influence the future, right? Even if I do something kind of meaningless, I don't know, like I'll tap the microphone right here. Maybe you might think that it doesn't affect the future at all, but maybe I exerted so much energy that it would require me to take a nap later in the day, and that would actually, have quite a consequence. Or maybe it would distract someone listening to this class because they hear a little bit of a noise, and then they won't attend the class, which would be, a horrible consequence. We wouldn't want to do that, so I apologize for that. It's actually really tricky to think of actions that don't affect the future. And here's a little example demonstrating this. So this is a double pendulum that is the same double pendulum, just recorded 6 times. It starts basically from the same initial conditions, or at least indistinguishable to us. And the initial action is the same. The person just lets it go. And let's see how it evolves. So we can see that the action seems fairly similar. The initial conditions seem quite similar as well. And initially, all of these recordings seem basically indistinguishable. It looks exactly the same. However, over time, the consequences with the slight difference in the initial action and the initial conditions compound quite a bit. And towards the end, all of these 6 recordings look completely different. The pendulum behaves in a completely different way. This is something that is well known in chaos theory. It's also referred to as butterfly effect. I encourage you to look it up. But that's just one example of how something that seems very small and doesn't really matter at the beginning, it actually can have quite large long-term consequences. And so far in this class, we've been talking a lot about supervised learning. And supervised learning is one of these cases, or the modeling in supervised learning is one of these cases where we pretend that the action that we'll take doesn't affect the future. All right? So for instance, we'll be classifying cats and dogs, and we'll be looking at the image, and based on what we see in the image, we'll say, this is a cat. And then in our modeling procedure, we pretend that this is the end, right? This is where the world ends. This is kind of the block world that we are in, and nothing happens after that. But in reality, you would make a decision whether this is a cat or not, and then this would have some further consequences, and you would use that information somehow. So supervised learning is this very kind of small, toyish world where we've been operating so far, and reinforcement learning allows us to make it a little bit more realistic and think about consequences of our actions. There's a lot of common applications of reinforcement learning because of the fact that it can model the world quite well, such as robotics, There's also a lot of reinforcement learning in language and dialogue, in autonomous driving, also maybe another example of robotics, in business operations, where we definitely have to think about long-term consequences, or in finance. So it's actually used in many deployed ML systems. And it's also one of the key aspects of intelligence, right? Like, this is how we make decisions. This is how we model our intelligent behaviors. We think about long-term consequences of what we're doing. So I think it's a little bit closer to intelligence as we know it. All right, so the plan for today's lecture is the following. We'll briefly talk about the reinforcement learning problem. I hope that this will be mostly the review, so we'll just briefly talk about the concepts and so on. Then we'll talk about one way of solving a reinforcement learning problem with policy gradients. And then, time permitting, we'll talk about Q-learning. It will be split into two parts, the prediction part as well as the policy improvement part. I don't think we'll be able to go through all of this today, but it might spill over onto Monday's lecture. All right, so let's start with the RL problem. And for this, we'll consider two cases: an object classification case that you're more familiar with. This is a supervised learning case. And an object manipulation case, where, let's say, an agent has to manipulating a bunch of objects. And this is an example of a sequential decision-making problem, a problem that reinforcement learning deals with. So in the supervised learning case, we could make an assumption that we have IID data available to us, right? It's in the IID data, which we can just take from a data set, and we just assume that the data is distributed in an IID fashion. In a sequential decision-making process, that's not the case, right? So when I perform an action, that action would affect the next state that I'm going to see. So because of that, depending on what action I'm taking, I will see a different data distribution afterwards. So it's clearly not IID. In addition, in supervised learning, we have these large labeled curated data sets that are just available to us, and we can work with them. But in sequential decision-making case, this is a little bit more tricky. There will be some cases that we'll discuss where we have data sets available to us, and we have to think about how they were generated and so on. But in general, we have to answer the question, how do we collect the data in the first place? Right? Since the data is not distributed IID, we are the ones influencing the data distribution, so we have to think how to collect it. And it's also a little unclear what the labels are for that data. Is it, are we labeling actions? Are we labeling the outcomes we want to achieve? Are we labeling with, what kind of modality do we use for this, and so on. In supervised learning, we also have a well-defined notion of success. We have our training and test error, and we can minimize that error, and that defines what we are trying to do. Versus in sequential decision-making, it's even not very clear what does success mean and how to define it. All right. So let's start with a quick terminology. So far we've been talking about a supervised setting where you, for instance, see an image and it goes through some kind of model, for instance, a deep neural network that is parameterized by some parameters theta. And we have to, at the end, we have to classify what's in the image. For instance, what kind of cat we are seeing in the image. Now, in our sequential decision-making process, first it will be dependent on time. But more importantly, the decision that we'll make will influence the next observation we're going to see. So there is this feedback loop here. Then in addition to this, we won't be just classifying what's in the image, but we'll be actually performing actions in the real world, actions that have consequences. So when we see an image of a tiger, the actions that we have to do, that we have to choose from, actually have real world consequences. And the next observation really depends on what action you'll choose here. So in terms of the notation, OT would be, we would use it for the observations that we see. AT is the action that we perform, all right? Then we'll have our policy, which we'll usually refer to as pi. It's pi parameterized with some parameters theta. These are the weights of the neural network, which gives us the probability of an action given the observation. So pi of AT given OT. Then we'll also have a notion of a state, and we'll talk about it in a second. And then we'll also have a policy that acts on the state as opposed to on the observation. This is so-called a fully observed case. So just to tell you a little bit about the difference between state and the observation, let's go back to philosophy. This is Plato's cave. This is a concept that Plato's described in some of his works. And the idea was the following. So Plato was basically thinking about how is it possible that even though we see objects that look very differently, we have these abstract concepts that we can refer to. For instance, even though you see 10,000 different tables, they all look very differently, you can still refer to a concept of a table, and people understand what you mean when you say a table. Right? So there's some general concept, some general idea of a table. So the way he was thinking about it, the way he thought it works, is that we actually don't get to observe the true reality, but we just get to observe a reflection of the true concepts in the world. So this is us sitting in a cave. There is a god behind us, or I guess multiple gods behind us, and then there is a godly fire behind us as well. And the gods are showing, presenting the true nature of an object that we don't get to see. And then we only get to see the reflection of that object projected onto the wall in front of us. And that projection, can take different forms. These are the different types of tables and so on. But we never actually get to see the true nature of what a table is. Right? The true nature is being hidden from us, but we can somehow refer to it, and that's how we can abstract these concepts. So using this analogy, what we'll be referring to as observation and state is the things that we see, the things that we can actually sense, or the robot can sense, are the observations. And they might not have all the data that we need to make the perfect decision, or they might have too much data. And the state is the true nature, the true thing that we need to know in order to make the perfect decision in the world. All right? So to make it a little bit more practical, an observation could be an image that we see. This is just directly what we sense. And then based on this image, we need to make a decision. And the state would be all the information that we truly need to make that decision, which would be, for instance, the positions and orientations and velocities of all the objects in the scene, and maybe the category of these objects as well. In addition, the observation may be incomplete, so we can have an occlusion. There could be a car in front of us, and we won't have all the information we need to make the optimal decision. All right. So we are dealing with this sequential decision-making problem. Let's think a little bit about how we can solve it using the tools that we already have. So I'll switch the example to a driving example. So let's say as input, we get an image from a camera in a car, and then as the action, we need to pick the steering angle and the acceleration, for instance. And we need to learn this policy, pi theta at of at given ot, so that we know what kind of action to take given what kind of image. So there is actually one way we can do this that we already know. We can just apply supervised learning to it. And this is what was done in NVIDIA in 2016. So what they did is they collected a bunch of data from human drivers, from truck drivers, collected observations and the corresponding actions that they were doing, put it in one big data set, and then used supervised learning to train that. So to train our policy that would then tell us what kind of action to take given a certain observation. So now my question to you is, what do you think could be a problem with an approach like this? Yep.
So it's always going to be the human against the input images. So if you square off because you're making a prediction and that's wrong, or not wrong, but where you square, you're going to have a hard time actually finding out what the wrong inputs will get you back onto it. Because in the next step, it's going to be the human driver who never would have made, never would have made that mistake, hopefully would make that mistake because he's a well stepper. You won't get the consequences of your actions that you've made. You won't learn how to correct them because you're always given, you have the bias.
That's right, yeah. So we'll have a lot of positive data that where the drivers drive, very comfortably and everything makes sense. But as soon as you make a little bit of an error, we won't really have that data to tell us how to correct that behavior. Yep.
There's also no temporal memory in this simple language.
Yes, there's no temporal memory. Yep, that's true. Is that a problem?
Yeah, if you like another truck comes to your side and that includes something that you should have been able to, that you should have used there. If you had like broken brain, because you're just like broken brain, you don't have to upgrade that piece.
Right. Yeah, that's a good point. Yeah. So if you, for instance, saw a track on the side, for instance, in a side mirror, and then you don't see it for a second, as a human, you would remember that there is still a truck there, and you shouldn't change your lane. Versus here, because you're seeing only one frame at a time, you'll immediately forget about this and potentially change the lane and result in an accident. Yep.
It can't really get better on the fly.
Yes, it can't get better. That's true. Yeah. We can collect more human data, and maybe with more data it will get better. But there is no kind of straightforward procedure that would guarantee that we'll get better with more data. Yeah. All right. Cool. So let's talk how we can do this with reinforcement learning. And in order to do this with reinforcement learning, we have to be able to tell whether an action is good or bad. Right? In the imitation learning, in the supervised learning setting, we could just say every action that the human did is a good action, and anything else, we don't even get to see. So we have to be able to decide which action is better. And in order to do this, we introduce a reward function. So a reward function would tell us which states or actions are better than others. So for instance, in the driving case, if we could assign high reward to the states that are desirable, for instance, we are driving smoothly, maybe fast, safely, and so on, and low reward to the states where they result in collisions. All right. Then all of these things, so the states, actions, reward function, as well as the transition dynamics that tell us how our world evolves, so the probability of next state given the current state and the action that we're going to take, define what we call a Markov decision process, which is the framework that we're going to use to in reinforcement learning and what we'll be solving in reinforcement learning. All right. So the goal of reinforcement learning is to train a policy pi theta. This policy that is parameterized by theta that maps from observations to actions. So as input, it takes observations. As output, it outputs actions. These observations actually is some result of a state that we don't get to see, right? Like there is something in the real world, and then we just get to see the image of it. And then the action and the state result in the next state that we get to see, and we don't really get to control these transition dynamics. This is the P of S prime given S comma A. This is just how the world works, right? Like given that I'm in a certain state and I'm going to perform a certain action, I'm going to see something, what's going to happen next. So that results in the next state, and that results in the next observation, and so on. So we can write it down as a probabilistic graphical model, where we have all the dependencies that we just described. So we have the state that leads to the observation. Then given the observation, we need to perform the action. And then given the action and a state at certain time step, given our transition dynamics, we can transport to the next state. So this part here is our policy, pi theta. And this part here is our transition dynamics, P of st plus 1, given st, comma at. Now, the important part is that the transition dynamics are independent of the previous state. This is the assumption that we make in the Markov decision process, and this is what we call a Markov property. So what that means is that to predict what S3 I'm going to see, I only need to know what S2 was and A2 was. I don't need to know anything about the past. Right? This is the assumption that we make, and that makes math much, much simpler. And this is actually quite important, and it's often difficult to make sure and think about that the system that you're working with is actually Markovian, actually satisfies this Markov property, where the transition dynamics only depends on the previous state and the previous action. All right. So for the purpose of this of today's lecture, and I think for most of the course, we'll make the assumption that we are in the fully observable world and we get to see the state itself. So we'll just say that the observations are basically our states. So we'll just get rid of the observations and we'll be mapping straight from states to actions. This would just make our notations a little bit simpler, and the whole problem is quite a bit simpler as well. So now let's start with a little bit of math. So given this probabilistic graphical model, I'm going to write down the joint probability of all the probability distributions that we see, random variables that we see in this graphical model. So this will be a joint distribution of all the states and actions from starting from time step 1 up to time step capital T. All right? And what this actually is, this joint distribution, is a trajectory. Right? So the trajectory is just a sequence of states and actions that happen one after the other. Now, given this graphical model, we can factorize this distribution as following. So we can start with the probability of starting with in S1. So this is the probability of our initial state distribution, times this big product of the probability of taking a specific action in that state, times the probability of then jumping to the next state, given the action that I just picked and the state that I was in. Right? And we can keep multiplying these up until capital T. Yep, there's a question.
So capital T with the probability of ST plus 1 for that form on the left-hand side?
Yeah, I think there we will just end with probability of the action at the very final step, and that's it. We'll just finish with that action. All right, so I'll be referring to this first term here, this joint probability distribution, as tau. And this is the probability. This is the random variable that depicts the whole trajectory. So tau would correspond to a trajectory. And now the goal of reinforcement learning is to find the parameters theta, right here. We'll be calling this theta star, which solve the following equation. It's the argmax of the expectation under our trajectory distribution, which we'll be referring to as pi theta of tau, of the future sum of the rewards that we are going to get. So what that means is that we have some kind of distribution of our trajectory, right? We get to control certain parts of this distribution, just this part. We only get to control the policy. We don't get to control the transition dynamics and so on. This is the only kind of knob we have. And under this, we then take the expectation under this distribution, and we want to maximize the sum of the rewards, right? So given that, well, our policy will result in certain trajectories, how can we pick the right set of parameters so that we maximize the sum of the rewards that we'll get? All right. And since this is a course about multitask and meta learning, it's important to think about what is a reinforcement learning task. So in supervised learning, we were calling a task a data generating distributions as well as the loss. In the reinforcement learning, a task is the whole MDP. So in that case, this will be the state space, the action space that we get to use, the initial state distribution, so the probability of S1, the transition dynamics, as well as the reward function itself. So the whole Markov decision process is a task. And it's important to note that this is much more than just the semantic meaning of a task, right? So whether you're just grasping or pushing, these are considered different tasks, but here we have much more strict definition of what a task is. So just a few examples of what different task distributions could be. So for instance, in character animations, where we have characters that have to do different tricks, this would correspond to different tasks because the reward functions between the different tasks will vary. We can also do character animations where we are trying to put on or animate how to put on a shirt or some kind of garment. And in this case, what would vary would be the initial state distribution as well as the dynamics. So every piece of clothing would have slightly different dynamics. We can also consider a multi-robot case where we're trying to learn a policy and gathering data from all kinds of different robots. And in this case, what would vary would be the state space, the action space. The robots will be controlled slightly differently, the initial state distribution, as well as the dynamics, even though they could be performing the exact same task and they could be using the same reward function. Right, are there any questions at this point? Yep. Yeah, so you can use that, and you can include that in your state.
Okay.
Yeah. So state doesn't necessarily just correspond to a position. State could be, in our case, could be even the whole image. Mm-hmm. Are there any other questions? All right. If there are no more questions, then let's talk about how we can actually solve it. All right, and we'll start with something fairly simple or fairly similar to what you've been doing before, and then we'll build on top of that and kind of see how we can get to more complex methods. All right, so there's this anatomy of a reinforcement learning algorithm that can help you to classify all kinds of different RL algorithms and kind of have provide like a mental framework that you can use to think about them. So this anatomy looks like this. We have 3 boxes. So we start with some way of generating samples. This is this orange box. So what that means is that we just run the policy, our policy pi, in the real world. We collect the trajectories. We can score them based on our reward function, and that's it. Then we have the green box here, where we fit a model to estimate the return, so the sum of the rewards. And here we'll talk about different options. We can just calculate the sum of the rewards. This is called the Monte Carlo, and this is what we'll be using in the policy gradient, which we'll talk about in a second. We can also fit a Q function. We'll also talk about it a little bit later. Or we can estimate a model that models the transition dynamics. This is also used, and you'll probably discuss it in the lecture, I think, on Wednesday next week. And then we have the blue box, which, given that we collected some samples, we can fit a model to estimate the returns. Now we have to have a way of improving our policy. And here we have a few different choices. So we can either take the direct gradient on the objective. This is what we'll be doing in the policy gradient case. We can also do an argmax on the Q function, which is what we'll be doing in the Q learning case, which we'll talk about. Or we can optimize the policy using other methods that people use in model-based learning by, for instance, backpropagating through the model or using a shooting method or something like that. All right, so we will take a look at policy gradients approach, which is the most direct way of optimizing the objective we care about. So just again, the objective that we care about is the following. We are trying to find the parameters theta that would maximize this expectation right here. So this is the expectation of the sum of the rewards, and this is the expectation under our trajectory distribution pi theta of tau. So I'll be just calling the pure objective, I'll just call it j of theta. Right? This is our objective that is dependent on our parameters theta. So our j of theta is equal to that. I just rewrote it. And now, because we have an expectation here, we can actually approximate this expectation, as we usually do in machine learning, with samples. Right? So in that case, we would take multiple samples. We'll take n samples, and we will take just the average. We'll be averaging, for every ith trajectory, we'll be averaging the sum of rewards. So what this is going to allow us to do is just to evaluate the objective. Right? We are not optimizing it yet. We just want to say, how well am I doing based on my objective? So what that means is that this expectation was under the trajectory distribution, so we are approximating it with samples. So what we'll be doing, we'll be just rolling out the policy multiple times. Right? So we'll be just allowing the robot to run a few times given our current policy. And let's say we'll collect 3 trajectories like this. Right? And in this case, n is equal to 3. Then we will score them, so we will calculate the sum of the rewards for each one of them. And then we would sum over those samples from pi, and that's it. That would tell us how good is our current policy. We'll take the average of all the trajectories that we rolled out, and that average is telling us how well am I performing on average, how good is my objective right now with my current policy pi theta. All right. So we can evaluate the objective. Now let's think about how we can improve on that objective. Right? So again, we start with our objective as we had it. And I'm going to rewrite this objective slightly as this. So our objective here, instead of having the sum of rewards, I'm just going to call it r of tau, which is the full trajectory. So this is just a shortcut notation, so it's a little bit easier for us, but it denotes the sum of all the rewards that we get for the trajectory. Right? So now the way we can write it out is we can write out this expectation, don't approximate it with sample, but actually use the definition of the expectation. And because this is a continuous distribution, we would write it out as an integral of our pi theta of tau times r of tau d tau. Right? So we have this ugly integral here, and we have to do something with it. But now we want to improve on that objective. And the way we usually improve on objectives in modern machine learning is we do gradient descent. Right? So we compute the gradient with respect to our parameters of the objective, and then we perform the gradient descent or ascent procedure to improve on the objective. So let's try to write out the gradient of our objective. So we can start by just adding gradient with respect to parameters theta of our objective, and we can actually swap the order between the integral and the gradient itself. These are two linear operations. You're allowed to do that. And now we have a little bit of a problem, right? So we have this very awful gradient. We have to integrate over all trajectories, and then we need to not only do this, but we also need to take a gradient with respect to all of this, and this is this distribution, the trajectory distribution, which we don't really get to control. So the first thing that we want to deal with is that this gradient, this integral is not tractable, right? Like we are not able to integrate over all kinds of trajectories. So when we have that, what we usually try to do is try to somehow change it back to an expectation. So let's try to do that. So what we will have in this case is that we have our let's just write it like this. We have our gradient with respect to parameters theta of pi theta of tau. Right? This is the first term that we have in that under that equation. And the way we would want to change it is that we would want to somehow pull the distribution of tau in front of the integral, so that then we can take the expectation, right? Because we have here some integral, here is our gradient operator, and then we have a bunch of stuff here, including our distribution pi theta of tau. And what we want to do is somehow pull that pi in here, because and this is d tau, right? Because if we do that, then once we have the integral, and here we have the probability distribution pi theta of tau, then we can just say that this is the expectation under pi theta of tau, right? And then we can just keep whatever was inside here in there. And once we have the expectation, we can approximate it with samples, and we're good. We don't have to do the integral. So now what we want to do is take that, what we have right now, and somehow change it such that we have pi theta of tau times some kind of gradient of something, right? So the question is, what is that something? So we have to do a little bit of arithmetic to get there. So let's try to do that. And to do this, I'm going to tell you about a certain identity that should come in very handy. So that identity is, I think you might be familiar with it. It's fairly straightforward. It says that the gradient with respect to x of log of f of x is equal to, can anybody tell me what this is equal to? You remember that? Yep.
Yeah. 1 over f of x times the
1 over f of x times the gradient with respect to x of f of x. That's right. Okay, a simple identity. So now what we can do is let's multiply both sides by f of x. So if we do that, what we'll end up with, I'm just going to write it here, is we'll have f of x grad x log f of x is equal grad x f of x. All right, I just multiply both sides by f of x. All right, so now we have an interesting formula here that actually gives us the answer to what we want. So we want to somehow transform this part, grad with respect to theta of pi theta of tau, to pi theta of tau times the gradient of something. So the part that we have on the left side here is what we have on the right side right here. Right? This is just instead of x, we have theta here, and instead of f of x, we have pi of tau, pi theta of tau. All right, so then the missing part here would be we have f of x, which is that part here, pi theta of tau. This checks out. And then we have the gradient with respect to x, gradient with respect to theta. The only missing part is the log of f of x. So in this case, this would be log of pi theta of tau. All right? So we just transformed it slightly, and this way, using this log trick, this simple identity, we can actually, so I'm just going to write this down right here. This is just, I'm repeating exactly the same thing that I wrote on the board. And this is how we can rewrite it, and this is just what we got to on the whiteboard as well. And now, given that, we can go back and roll it back into an expectation, right? So now we have the integral, and under our integral, we have a probability distribution of tau, d tau. So we can use the definition of an expectation and roll it back into the expectation and just say this is the expectation under the distribution of pi theta of tau of the term that was inside in there, which is this grad log pi times r. All right. So what we did so far is we came up with a formula that gives us the gradient with respect to our objective. And we got rid of this integral that was a little nasty. So there's one more piece, right? We had two nasty things. One was the integral, and the other thing was that we have this pi theta of tau, which is the whole trajectory distribution. And we don't really control the whole trajectory distribution. We only control the policy. This is the only part that is dependent on the parameters theta. So let's just write it out. So this is our pi theta of tau. This is just, I wrote out the whole tau, and this is the factorization that we had before. So this is pi theta of tau. And let's take the log of both sides because we need the log here. So if we take the log on both sides, we see that the log of the product is the sum of the logs. So we do that. And now we can just substitute whatever we got here under here. So let's do that. So we are substituting this log pi theta of tau with all the terms that we used in the factorization. So this is now the initial state distribution, our policy, and the dynamics, right? And our policy is the only part that is dependent on the parameters theta. And we take the gradient with respect to theta of that, right? So if we do that, can you tell me what would be the gradient of this term with respect to theta? 0, that's right. And what about this term? 0 as well. Yep, that's right. These two terms are not dependent on theta. We take the gradient with respect to theta. These are 0. They cancel out. And what we end up with is a formula like this, where the gradient with respect to our objective is just this expectation under our trajectory distribution, pi theta of tau, of the sum of this grad log pi. And this we can actually evaluate, right? This is our neural network. This is the neural network that, given an input, a state, outputs an action. We can take the log of that, compute the gradient. That's OK. And we then multiply it by the sum of the rewards. All right. So now we have a way of actually having a gradient of the objective, so we can now improve on our objective. So let's try to evaluate it first. So the same way as we are evaluating the objective, how would we evaluate the gradient of that objective? So I just rewrote the formula and recall that we were able to before approximate the expectation with samples from our trajectory. So let's do the exact same thing here. So we will be approximating this gradient with a bunch of samples. These are samples from our trajectory. So we'll have n different rollouts, and we'll be averaging over these terms for each one of these rollouts. And then once we do that, then we have our gradient, and we can perform our gradient ascent procedure to improve our parameters so that our objective gets better and better. Right. Are there any questions at this point? Yep.
Given the rollout, is the difference between it due to like the Markov and probabilities?
Could you repeat the question, please?
What explains the difference between the trajectories?
Oh, I see.
Like an initial.
Right. So how is it that if you roll out a single policy, it results in 3 different trajectories? Yeah. So there's multiple differences. So first thing what could happen is that your policy is stochastic, right? So the policy is a probability distribution of actions given a state. So then according to those probability distributions, you'll be picking slightly different actions every time. That's one thing. The other thing is that the dynamics itself can be stochastic as well. Right? So given a certain state and action, sometimes it will result in a certain S prime, sometimes it will result in a slightly different S prime. And this would correspond to differences in the way you roll out the policy, and this will result in different trajectories. Right? Are there any other questions? All right, cool. So what we did here is, in terms of the anatomy of our RL algorithm, we have the generate samples part, which is the part that we have here. We just roll out a bunch of policies a few times. Then we fit a model to estimate the return. So the green box in our case is this. We just sum the rewards that we got for these trajectories. And then to improve the policy, the blue box, we are just doing the gradient ascent procedure. We compute the derivative with respect to our objective, and we do gradient ascent, and our policy gets better. And this results in one of the simplest RL algorithms called reinforce. And it works exactly how you would imagine. We sample a bunch of trajectories, so we run the policy. Then we compute the derivative with respect to our objective according to our formula that we just established. And then we perform gradient ascent, and we do it over and over again. Right? So then we improve our policy, then we roll out this new policy again, and we keep going. Right. So just one quick side note here. We also talked about imitation learning, right? And in imitation learning, what you would do is you would do maximum likelihood. So the policy gradient formula is written right here. This is what we just discussed. But in the imitation learning case, which we discussed, where people from NVIDIA were just collecting the data and trying to fit our policy to be to replicate what the human drivers did. The objective would be to maximize the log likelihood. So we were trying to maximize the likelihood of our data given the model. And the objective would actually look like this, and it would be very, very similar to the objective you see up here that we just derived with the policy gradient. So could you tell me what's the difference, or how can we make the policy gradient look exactly the same as the maximum likelihood? Okay, so how can we make our RL algorithm behave exact same way as an imitation learning objective? Yep.
You give it constant reward.
You can give it constant reward. What kind of reward?
Like I'm just looking at the equations up there, and if R was always like R like independent of SIT or AIT, then it would become the same as the maximum likelihood.
Right, so the reward would need to be constant, but it would need to be constant for specific actions, the same actions that the humans did, right? Yep. That was what you were about to say? Okay, yeah. So we would need to reward the actions that the humans did, let's say with the reward 1 at the very end of the trajectory, and every other action would be 0. And in this case, the policy gradient would correspond exactly to doing imitation learning. All right, cool. So a little bit of intuition of what's happening here, if you maybe got lost a little bit in the math. So we have our reinforce algorithm, we have our objective. This objective is fairly similar to the maximum likelihood objective. But what that actually means is that we would look at our trajectory distribution. We would roll it out. So that would result in these 3 trajectories, let's say. So our trajectory distribution will look like this heat map that you can see underneath, right? So certain trajectories will be more likely than others. And then through our policy gradient, we would shift our probability mass towards the trajectories that achieve higher reward, right? So it's dependent on the sum of rewards right here. So the trajectories or the actions that result in higher rewards would increase their likelihood, and actions that result in lower rewards will decrease their likelihood. Right? So then we would change our trajectory distribution to move towards the trajectories that achieved higher returns. So basically it makes the good stuff more likely and the bad stuff less likely. It just formalizes the notion of trial and error. It just formalizes it mathematically. All right, so to summarize, the pros of policy gradients is that it's fairly simple. It's easy, because of that, it's fairly easy to combine with existing multitask and meta-learning algorithms, and we'll talk about it in the next class. And in terms of cons, the gradient that you see here, you can barely see my pointer. This gradient, this estimate of this gradient actually has very high variance. So people usually use various tricks to reduce that variance. So in practice, it's usually used with so-called baselines. People use stress regions and all kinds of different tricks to make it better. But it also requires on-policy data. And what I mean by this is the following. So this expectation here is with respect to the trajectory distribution induced by our current policy pi theta. Right? So we iteratively have to be running our current policy all the time. We can't really look at the data that we generated in the past. We can only look at the data that we generated right now. The policy is improving with every iteration. So we cannot reuse existing experience to estimate the gradient. We can only use the current experience, which is actually a really big limitation. And this is something we'll discuss a little bit more. We can sort of do it with importance weights, but it produces even higher variance, and this is quite tricky to get to work. All right, so to just briefly tell you what's on policy versus off policy, the on policy means that the data has to come from the current policy, as it is in the policy gradient case. It's compatible with all RL algorithms, so any algorithm you'll learn about, it's possible to run it on policy. So that means you're generating the data and then you're using that data that you just generated to improve that policy. But it cannot reuse data from previous policies. So you can only use the data that you just generated with your current policy. As opposed to off policy, where data can come from any policy, and we'll learn about it in a second. It works with specific RL algorithms, with value-based reinforcement learning algorithms. And it's much more sample efficient, because now we can do gradient steps on the old data as well. So we can be reusing the data many, many times, as opposed to just running the policy once, generating the data, and you can only use the data in this moment, and then you will improve the policy will change, and you have to generate the data again. All right, so are there any questions regarding policy gradients? Yep.
I'm curious, can we change the sampling strategy, like sample the trajectory from your policy to from uniform sampling to some prioritized sampling? How do you call that on policy?
So the question is, if you change
like the first expectation, the trajectory. Yeah.
I see. So what would happen if you change that expectation to be under some other distribution? If you change your sampling strategy so you sample from something else, would that
still make it work? Current policy. I just changed the sampling strategy, like from uniform sampling to some prioritized sampling.
I see. So if you change your sampling strategy, but you would still use the current policy, I think what that would mean, if you mean like you would just do uniform sampling of trajectories, that's not really feasible to do, or you would have to have a uniform policy then, right? So the policy would assign the same probability to every action it can perform, and then that would be the uniform sampling strategy of trajectories.
But then
you're changing the policy.
I use my policy to generate 3 trajectories, and I sample those 3 trajectories with same weights, and I call that kind of sampling like uniform sampling. Mm-hmm. But another kind of prioritized sampling is I assemble weights to more recent trajectory. I see, yes.
I see, okay. So you would still generate the trajectories the same way, but then you would use them to estimate the expectations differently. Yeah, so you can do that, and usually people do this with importance sampling, which tells you exactly how you should change those and how you should sample them so that you adjust for the probabilities of your current policy, but that results in even higher variance. So that's tricky to do, but yeah, it's possible. Yep.
What happens if you get a trajectory that's like not very common because it's making good trajectories more likely, and so if you ever get to a trajectory that's not very common, you wouldn't really know what to do. I feel like in other algorithms you can have noise to increase the exploration, but then if you do that in this case, it wouldn't be policy.
Yeah, this is a great question. So just to repeat the question, you're saying that in this case you can't really change the policy that you're doing the rollouts with. You can't add noise to it or something like this. And if you just, by luck, you're just got really high return for that particular policy because you just rolled it out once, then you would you would shift your probability mass towards that policy, even though you were just lucky. And yeah, this is the problem with high variance. So you're just estimating the entire objective based on few rollouts or a single rollout in this case. And if you're just lucky, then you didn't estimate that gradient correctly. And then you'd shift the distribution mass towards the thing that you shouldn't be really shifting it. And we'll talk about how we can improve on that. Yeah, this is a great question. All right, cool. All right, so we talk about off-policy and on-policy. So there is one more small note that I wanted to make here. So let's take a look at our formula here again. This is our policy gradient formula. And I'm going to make a slight transformation of this formula here. So what we are doing here is we are summing a bunch of terms in this parentheses. And then we are multiplying it by a bunch of terms that we are summing as well in this parentheses. So basically this corresponds to something like this. We have A plus B plus C, right, times X plus Y plus Z, right? So what we can do instead is we can rewrite this as A times X plus Y plus Z plus B times X plus Y plus Z plus C times X plus Y plus Z, right? So this is just a slight rewrite. Right, so let's do that here. What this would result in is we'll be summing over, where's the pointer? Let me just show it with my hand. So we'll be summing over all of these terms, and each one of these terms will be multiplied by the sum of the rewards. Right, this is the exact same transformation that we just did on the whiteboard. Right, so let's do that. But now there is one thing that is a little peculiar. So we are summing for a particular action that we took at a certain time step t for a trajectory I. We will be evaluating this, and we will be potentially increasing the likelihood of that action based on the sum of all of the rewards that we achieved for that entire trajectory. So starting from time step 1 up until the end. Right? So in other case, we have this whole trajectory that we are looking at, and we are in a particular point in that trajectory, let's say in this green point right here. Right? And now we are summing all of the rewards that came before that we are taking this action, and what the rewards that came after we took that action. And we use that entire sum to tell us whether this action was good or bad. Right? Can anybody tell me what's wrong with that? Yep.
The action should only be based on, it should only roll out from that point in time. That's right. Based on what we did in the time.
That's right, yeah. So the action that can't really control the past, right? Like it only influences the future. So what we can do instead is we can just sum together the rewards starting from that action moving forward. And this would actually reduce the variance of our estimate. So we can do this slight change, and instead of summing the rewards at time step 1, we can sum the rewards starting at time step t, at the recurrent time step where we're at. And this is what we call the reward to go. So this is how much more reward there is left starting from this action up until the end. Right. Yep.
The two will be the same, right, in expected value?
Yes, but the variance of the estimate would be lower. That's right. All right, so this summarizes our policy gradient part. And now let's talk about Q-learning. So this would allow us, we'll talk about off-policy algorithms where we don't need to have this assumption where you have to roll out the policy and you can only use those samples to improve it. And it's generally a very exciting area of reinforcement learning research, and it's used all over the place, and it's very commonly used in robotics, where we very much care about data efficiency, and we want to take multiple gradient steps over the same data. All right, so we talked about the anatomy of reinforcement learning algorithm, and we talked about one particular way of doing reinforcement learning, which is with policy gradients. So directly optimizing in the objective, doing the gradient ascent procedure, and this is how we can approximate this gradient. And this green part here corresponded, or the sum of rewards corresponds to the green box, where we are trying to fit a model to estimate the return. Here we do multiple rollouts that corresponds to the orange box, and the whole thing corresponds to improving the policy. This is the gradient ascent procedure. All right, so now let's think a little bit how we can improve on that policy gradient. And the exact way I would like to improve is by improving the green box. So we'll try to improve that estimate of the rewards to go. All right. So let's call this some kind of estimate. We somehow need to estimate what kind of reward we are going to get starting from a current time step up until the end if I continue with this policy. And let's call this estimate the estimate of the reward to go, Q hat for the particular trajectory I at the specific time step t. So this is the estimate of expected reward if we take a specific action AIT in a state SIT. Now, can we get a better estimate of that rewards to go than what we are currently doing? And for this, let's go back to our little trajectory plot. So right now what we are doing is we are summing together all of the rewards starting at our green dot up until the end, and we're summing the rewards that we got from this trajectory that we are actually executing in the world. Right? So this is how we are just summing the rewards that we got for that specific trajectory. All right, so let's now imagine that we are trying to do this for our life. All right, so let's say you're trying to evaluate certain decision that you made in your life. Let's say you decided to apply to Stanford. All right, and now you want to estimate how good was that decision. Right? And the way we want to do this, or the way we are doing it here, is that you wait until the very end of your life, and then you look back at all the rewards that you gathered, starting from the decision that you made to apply to Stanford up until the very, very end. You're on your deathbed thinking about this. And then based on the sum of these rewards, you can now tell, was that action good or bad? All right? So there is this movie, and I apologize for spoilers. I don't think that's too big of a spoiler, but let's just think about this movie. There's this movie called About Time, where the main character, I think his name is Tim, he gets to travel in time. All right, so I think the way it works is that he just needs to close his eyes and close his fists really hard, and then think of a moment where he wants to get back to, and then he can just live his life kind of again from that moment on. All right? So now, if Tim were to evaluate his decision to apply to Stanford, what he would do is that he would go back to that point where he made the decision, or to the time step right after this, and live multiple lives, right? So live that life many, many times, and kind of go to the very end, calculate all of the rewards, and then teleport back in time to the decision when he decided to apply to Stanford, and then live that life again. So his estimate of the rewards to go would be much, much better than yours, right? Your estimate is just based on your life, and maybe, there was a little bit of luck involved, and your life turned out to be an amazing life, but it actually didn't have anything to do with you applying to Stanford. You were just maybe, you won a lottery a little bit later, and it just, seemed like this was an extremely happy life, and you thought that the reward to go was very high, but it's just because of the stochasticity of the dynamics. But Tim would be able to live that life many, many times and kind of integrate out all the little lucky and unlucky things so that he can actually tell what's the reward to go if I apply to Stanford. All right. So Tim can estimate the future sum of rewards. This is still with respect under the expectation of Tim of pi theta. So he still lives as Tim every single time, right? Like he doesn't make random actions after this. He's just Tim, so he behaves like Tim the entire time. So, but his estimate of the rewards to go is much better than us, right? Cool. So we called the Q hat the estimate of the expected reward. So let's call Q the true expected reward to go, right? So this is actually the true under the expectation under our current policy of the rewards that of the sum of the rewards we're gonna experience. And now if we could do this, if we could somehow get a better estimate of the rewards to go, then the entire gradient estimate would be better, right? So because we would be improving on this, the whole gradient would be better. So basically, Tim not only would be able to better estimate, how many rewards are there to go based on the decision, but he would also be able to make better decisions. All right. So now let's introduce 3 concepts here. So first, this function Q that we were talking about, which is the estimated, the expected sum of rewards. Let's continue calling it Q, and this would be the sum of the rewards under the expectation of our current policy, given that we start at a certain state doing certain action. So this is the total reward that we would get from taking action AT in state ST and then following our policy. So in fact, we shouldn't just call it Q, but this Q is also dependent on our policy. So let's call it Q pi. So this is the Q function, given the current state and the action we're going to take, and then we continue acting according to our policy. Tim continues being Tim. Yep, there's a question.
Like, based on the way we structure the reward, is the total time fixed, or people just get to keep, does actors get to make decisions and collecting new states for as long as they your best state or something?
Right.
They usually determine the reward.
Yeah, that's a good question. So the question was, do we get to act for a certain number of time steps, or do we get to act up until the very last state or some kind of final state? And these are 2 different formulations, and you can do either one. You can do the time-based version where you act for a certain number of time steps, capital T, or you can do the infinite horizon reinforcement learning, where instead you introduce a little discount factor that allows you to deal with the math. Cool. All right, so we have the Q function. Now let's introduce also another function, V. We'll call it the value function. And the value function would be just the expectation of our Q function according to our policy, under our policy. So it's very similar to the Q function, except the Q function, you had the choice of picking any action you want at the current time step, right? The Q function is dependent on that action. So Tim can decide to apply to Stanford, do something else, I don't know, do something completely random and so on. But after he makes that decision, he just continues acting as Tim. He doesn't have any freedom anymore. Versus in value function, Tim gets to teleport to a certain state and he gets to act as Tim straight away. He can't really try different things and do something completely random that is very unlike Tim. All right. And then we also have the advantage function, which we call a pi of st, comma at, which is just the difference between the 2. So it's the difference between the Q function and the value function, and that just tells us how much better is the action AT compared to the standard action that the Tim would have taken, right? So this is just how much better is action AT compared to the action that the policy would have picked. All right. So now one way we can rewrite our policy gradient is rather than summing the sum of the rewards that we got for the particular trajectory, we can use the advantage function or the Q function or something like that. All right. All right, so now in terms of the anatomy of our algorithm, what we are changing is that we are still generating samples, but to fit a model, we will now fit a model to estimate the returns. We want to just sum the returns, the rewards that we got for that specific trajectory, but instead we'll try to fit our Q function, value function, or the advantage function. We have these three things that we can use that help us estimate the future rewards. And then to improve the policy, we'll continue doing our gradient ascent procedure. All right. So, we just introduced these three new concepts, so I wanted to run a little exercise to see if that makes sense. So the exercise is the following. You're this little stick figure, and you start at some ST, and your dream is to become a drummer, right? And what that means is that you will be evaluated a month from now on this drummer test, and you get a reward equal 1 if you can play it, and if you can play it in a month, and 0 otherwise, right? So you'll be evaluated in a month on how good are you at achieving your dream of becoming a drummer. And now you have 3 actions that you can do. One action is just chill, don't do anything. The second action is that you can watch other drummers perform. You can watch videos of them and try to learn from that. And the third action is you can actually practice drumming. Right? You can play and try to get better that way. Then your current policy is the following. Your current policy is that you always take action A1. You always want to chill. Right? And all of the probability masses for that action. So you will always do that. So now my question is, what's the value function v pi of st? Yes?
And most likely it's going to be 0 if you always need to chill, given that you want to be able to perform time.
Right, yeah. So the value function is most likely 0 because you want to be able to play. Yeah, unless you're super good, then you can, yeah. Yes?
It's just one possible clarification. So what you mean by if I can play, is it a deterministic transition of me if I don't practice and I wouldn't be able to play that? Is that deterministic or is it stochastic?
Well, let's consider this in real life, right? So like you're being born right now, and these are the actions you can do at your current, so the t is equal 0, or maybe that shouldn't be in a month, that should be in like 10 years or something. And then the reward function itself is not stochastic, right? The reward function, given a state and an action, so given you playing the drums, can tell you, did you play it or not, right?
It can give you a reward 1
or 0. Sorry?
Transition.
I see.
Yeah, so the probability of you can't play that even you don't practice. Yeah, is that equal to 1?
Right. Yeah. So for the purpose of this exercise, we would assume that. Yeah. So there's no stochasticity in your transition dynamics that somehow by luck you can play it. Yeah. Or you would just like randomly play the drums and somehow it ended up being that you played what they asked you to play. Yeah. The probability of that is 0. Yeah. All right. Cool. So the value function is 0. Now what's the Q function? The Q of pi. Could ask somebody else, maybe. Yes?
What is 18 in this case?
What is 18 in this case? Yeah, and that's part of the question. What do you think it is? So you have to, the answer is a little bit longer than just the value function case. Yeah? 0.001.
Would it be a list or like a floating point value?
It will be a floating point value. So Q function just tells you the predicted sum of future rewards, right? So this is just a single scalar. Yeah. Yeah.
It'll be 0 for all actions because even if you choose to play drums at this state, you always go back to the next state which was subject to
Right. Yeah. So the answer that you gave was that it would be 0 for all the actions. So what that means is that the Q for st, at, where at equals a1, would be 0 because it will be exactly the same as the value function, right? You continue doing nothing, you continue chilling. If it was a2, so Q pi of st comma a2 would be maybe a little bit higher, but over 0. Maybe you'll learn like a tiny bit. Maybe there's a tiny bit of probability that you somehow learn how to play it, but you're saying probably not. It's 0 again. And now a3 means that you only decided to play in that time step, right? You decided to practice this one time step, but after this you continue acting as you with your policy pi, which is to always chill. So that means you decided to practice once and then you chill afterwards. So you're saying it will still be 0. Let's give it the benefit of the doubt. Maybe it will be a little bit higher, right? You at least practice once. Yep.
So the Q function is one number for each action you can take?
That's correct. That's correct. So given a specific state and a specific action, it's one number. Here, because we are choosing between 3 different actions, we have to say, for that action it will be this number, for this action it will be that number, for that action it will be a different number. Okay. So the Q function kind of thinks about the immediate action that you can take, and then you act according to your policy afterwards. All right, cool. Now, one more question, what's the advantage function? So a pi of st comma at. Yeah?
Same as the Q function with value function 0?
Yes, so it would be the same as the Q function because the value function is 0. So the advantage function is the difference between the Q function and the value function, right? So because in our case the value function was 0, it would be exactly the same as the Q function. Right. Does that make sense? Are there any questions on that? All right, cool. All right, so there's one more thing that I wanted to ask you about. So, before we were talking about summing together the rewards from the trajectories that we actually experienced. Now we talked a little bit how we can do this a little bit better, like kind of Tim, how Tim was doing this. But Tim still had to live his life till the very end to evaluate that action that he took, sometime in his 20s, let's say. So let's consider the game of chess. And in the game of chess, let's say you get a reward 1 at the very end if you win, and reward 0 if you lose. And what we discussed so far just talks about predictions, right? Like how well can you predict the sum of the future rewards? So how well can you predict whether you're going to win in chess match or whether you're going to lose? And so far what we've been talking about is that, how every time you would update your predictions, you would have to wait until the very end of the game to tell whether, to update your belief about the game. You would have to wait, you make a move, and then after you made that move, you have to wait, continue playing the game, and until the very, very end, once you get all the rewards, you get the reward 1 or 0, you'll be able to tell, oh, well, I was wrong, right? But that's not actually how it works, right? So, what happens if you don't finish the game? What happens if you made a move, right? You thought that it was a good move, and but to update that prediction, that model of yours, you had to wait till the very, very end. But let's say you went until the very, very end, except for the very last move, and the power ran out or something. And you never finished the game of chess, but you were just one move, away from being checkmated. Right? So you're about to update your belief, but you never finished the game. So, sorry, you don't get to update your prediction. So in reality, we don't always wait till the end, right? Like you can update your prediction right after you made that move, right? So like you made a move and then you realize in the very next moment, oh, I screwed up, right? Like my probability of winning actually went down significantly. I don't have to wait till the very end of the game. I can update it immediately after the move. All right, so let's try to do that. And we'll do this on the example where we're trying to actually learn the value function. So we'll try to learn it using supervised learning. So we'll do supervised regression where we have our value function, which is a neural network that takes as input some state, outputs a single scalar value. It's parameterized by some parameters phi. And we need some kind of target labels for that value function. All right? All right, so this is our value function. It just has a single output, a single scalar. So now our ideal target would be the true expected sum of rewards given that we start at a certain state, right? But we don't really have access to that. Now the Monte Carlo target, what we've been using before in policy gradients, would be just the sum of the rewards that we got for that specific trajectory up until the very end. All right? Now, one thing that we can see is that we can approximate this, and this is actually a very good approximation, with the following. We can take the reward that we got at the current time step plus the sum of the rewards, so the true rewards to go, the true expected reward, starting from st plus 1. Right? So this is kind of like our value function is equal to the reward that I got in this state plus the state that I actually experienced in my trajectory and the expected value from that state. Now, can anybody tell me why this is an approximation here? Any ideas? Yep?
This is not infinite time step. So this is a finite time step, actually, this is not
right, so this is a final, you're saying that this is a final time step problem, so we have a final number of time steps. Yeah, that's not exactly it, right? Because it would still work, even though we are summing, over a certain number of time steps t. This should still work, right? Like, regardless whether this is an infinite horizon or a finite horizon. Yep.
We need to make some, like, for it to be exactly the same, we would have to put in, like, for action A of IP, it would have to be probabilistic given our actual policy. And
Yes, that's correct. Yeah, so basically the approximation is here because this st plus 1, this is the state that we actually experience in our trajectory, right? So it's kind of like, let's go back to Tim example. What Tim would do is he would perform one action, right? He would teleport to a certain moment in time. He would take one action, and then he would say, let's calculate the value of everything that I've done after this, and let's just say that it's equal to my value at the previous state is the reward that I got, plus everything that I experienced after this single action. But he still just took this one action, right? Like, we still just teleported to the next state. And this is from the actual trajectory that we've experienced. So this st plus 1, this is a small approximation that we're doing here. Right. Now, one thing that we can notice is that even though this is an approximation, it's not too bad of an approximation. We're just making this one step. We just think that we took this one action and we experienced a certain st plus 1. But we can notice that this part here is actually the value function at the next state, right? At the state at the next time step. So this is a little recursive, right? The target at the current state is equal to the reward that we got at the state plus the value at the next state. And we can approximate it actually even more, or actually it will be a less accurate estimate by saying that this would be equal to the reward at the current time step plus the value that we right now have, our fitted value. So v pi with the parameters phi of st plus 1. So basically we'll be fitting this over and over, and then we'll be using that estimate, that neural network, to give us the label for the previous state. All right. So in that case, our training data would be the state, and the target would be the reward plus the value, so what we actually are estimating at the next state. Right? So this is a little recursive, and this would be our target, and this is what we would sometimes refer to as the bootstrap estimate. We're estimating the value function, bootstrapping it from itself. Cool. And a few examples. This is actually this policy evaluation, this estimating value function has been used many times. Originally, it was used in the game of backgammon, where the reward was the game outcome, whether you win or lose, and the value function would correspond to the expected outcome given a board state. So we would look at the board, and the value function will tell you how likely it is that you're going to win. It was also used in the exact same way in AlphaGo, where computer was playing against the human champion of Go. And the reward was the game outcome, and the value function was exactly the same. It was a neural network that, by looking at the board, it was able to tell you, are you going to win or not, right? And the value function was fitted in this way. Cool. So we had our reinforce algorithm that we were using before, where we were just rolling out the samples and then we were estimating the gradient, and for this estimation we were using the sum of the rewards that we have experienced. And now we arrived at a slightly different algorithm, which we call an online actor-critic algorithm. So in that case, we will take the action according to our policy. We'll update our value function using the target that we just described. So the value function of the current state is equal to the reward plus the value function of the next state. And here it's a little discounted, but you can ignore that. This is to deal with the infinite horizon RL. So we are fitting the value function. Then we can evaluate the advantage function, and we can do this by just saying the advantage function of S, A is equal to the reward for that state in action plus the value at the next state minus the value. So this is our Q function, in other words, minus the value at the current state. And given the disadvantage function, we can now compute this gradient a little bit better because now we have a better estimate of the rewards to go. And this is what we can use the advantage function for. And we can perform gradient descent, or gradient ascent in this case. All right, cool. So this is just the prediction part, and we're going to end right here. Are there any questions? Yep.
You guys classify S is still on policy, right?
Yes, this is, so you can estimate the advantage of policy, but you have to do this step on policy.
How would you estimate the advantage of policy? Because you still need to get the V of I.
Yeah, so we'll talk about it on Monday. Yeah, that's a great question. Right. Are there any other questions? None? Okay, cool. So yeah, on Monday we'll talk about how we can actually improve the policy using these concepts, and hope to see you there. Thank you.